Alright, let's consider an angle in standard form. So once again, the standard form or standard position of an angle is where we have one arm that's positioned on the positive x-axis. It's called the initial arm, and I've kind of highlighted that in blue. And the other arm is going to be either on the positive x-axis or away from the positive x-axis. So I've kind of shown that in red, and in red we have something called the terminal arm, and in blue we have something, the arm or the ray is called the, whoops, I wrote blue out, it's called the initial arm. Okay, and we know that the angle is a counterclockwise rotation if it's a positive angle, and for the time being we're going to look at positive angles. Now we can look at the end point of the initial arm as a coordinate in terms of x and y, and this is actually a way to position for us to describe the position of the terminal arm and thereby discuss what the angle could be created between the initial and terminal arm. So we're looking at this point of the terminal arm. We can understand here that this is the y coordinate, this is the x coordinate, and if we do a full rotation, right, if we do a full rotation, and if I draw this to scale actually, we can understand that the vertex in standard position of the initial and terminal arm would be the origin, 0 and 0. If we do a full rotation, this actually becomes the circle. So the length of the terminal arm thereby becomes a radius. Now we're going to look at a special type of circle called the unit circle, which we kind of looked at earlier. A unit circle basically has a radius, right? The length of the terminal arm, the radius is 1 unit. Okay, it makes us, it's just a lot easier to kind of approximate some of these values. So if the radius here is 1 unit, if I looked at the ratios of my angle theta, we can understand that x and y are 90 degrees apart, right? Because the x and y dimension are perpendicular. So because these are 90 degrees apart, we essentially create a right angle triangle. So because we have a right angle triangle, we can determine our primary trig ratio. So I'm going to figure out what my 3 primary trig ratios are. And once you find your primary trig ratios, you can also find your reciprocal trig ratios. Now if I look at sine theta, we can notice that sine theta is the opposite over the hypotenuse, which is y over r. Because we stated that this was in fact a unit circle, then we know that r here is 1. So this is basically y over 1, which is y. Cosine theta here is going to be adjacent over hypotenuse, so x over r. R is 1, so we're going to get x over 1, which is x. And tan theta is basically, in this case, y opposite side over the adjacent side, y over x, which in this case is sine theta over cosine theta. This actually brings up a really important identity, and this is called the quotient identity. So we're going to be using this really important identity later on when we actually prove identities. Okay, so this is kind of like a precursor lesson to the next set, which we're actually going to be solving and proving for identities. So the quotient identity states that tan theta is sine theta over cosine theta. I might have shown you guys this in previous videos, so kind of review that. But just so having said this, we can understand that this triangle here is in fact a right angle triangle, and because it's a right angle triangle, we can also employ Pythagorean theorem. So therefore, a squared plus b squared is equal to c squared, and c is usually the hypotenuse, right? And the hypotenuse is always across from the right angle, and in this case, c squared is r squared, so therefore we can also associate this with x squared plus y squared is equal to r squared, right? So using this notion, if we actually apply Pythagorean theorem and we apply our primary trigonometric ratios, we can understand that x squared is in fact cosine theta, x is cosine theta, so x squared is in fact cos squared theta. Y squared therefore would be sine squared theta is equal to r squared. We know that r is 1 in this case, so therefore one of our equations is cos squared theta plus sine squared theta is equal to 1. Now this statement that I made here, this equation, this is called an identity. That means that it's always true. And we can understand that when you have cos squared plus sine squared theta, it's always going to be equal to 1. And you can actually, you can basically play around with this equation. We can also understand that cos squared theta is equal to 1 minus sine squared theta. If you move the sine squared theta to the other side. And you can also see here that sine squared theta is equal to, if you move the cos squared theta to the other side, 1 minus cos squared theta. So this is one of our Pythagorean identities, right? And the reason we call them a Pythagorean identity is because we actually utilize Pythagorean theorem to determine this. So this is an identity is any statement that's always going to be true. We're going to be using this later on to basically solve for identities. Now, we also need to kind of consider the quotient identity. But there's two more Pythagorean identities that I want to also describe. And in order for us to kind of look at this, what helps to kind of do here is to also determine our reciprocal ratios. So if sine theta is equal to y over 1, or y, then cosecant theta, which is its reciprocal, is basically equal to 1 over y. Secant theta, which is the reciprocal of cosine, is equal to 1 over x. And cotangent theta, which is the reciprocal of tan theta, is cos theta over sine theta. Okay, so keep this in mind, right? And now what we're going to do here is figure out the other two identities. So if we take a look at our initial statement of the Pythagorean theorem, so I'm going to highlight out in white here, if x squared plus y squared is equal to r squared, if I divide everything this time by x squared, you notice that you get 1 plus y over x squared is equal to r over x squared. Okay, so 1 plus y over x in this case is, you can notice here, it's basically tan theta, right? So now it's tan square theta is equal to r over x in this case is basically going to be, and we can notice that r in this case is 1, so 1 over x here is basically secant squared theta. Okay, let me just clean that up a little bit. Okay, so this is going to give us secant squared theta. Okay, so this is yet another identity, call this identity 2, right? So 1 plus tan squared theta is equal to secant squared theta. Okay, so this is our second identity. So this statement will always be true, and you can also play around with this equation. You can solve for tan squared theta, right? Tan squared theta, if I move the 1 to the other side, it's equal to secant squared theta minus 1, and so forth, right? So you already know what secant squared theta is equal to. So this is going to be really useful when we're doing different types of substitution. In the last case, I'm just going to do it out here. What we're going to do here is, using the Pythagorean theorem, r squared, I'm going to divide everything by y squared. Okay? So if I divide everything by y squared, you can see that whatever you do to one side, if you repeat it to the other side, it keeps everything constant. So this is 1, so this is x over y squared plus 1 is equal to r over y squared. X over y in this case, we can understand here, is basically cotangent theta, right? And cotangent theta is going to be the opposite of tan theta, so it should be x over y, right? So we have cotangent squared theta plus 1. R over y in this case is basically going to be 1 over y, which is equal to cosecant squared theta. Okay, so this brings up our third identity, right? Cotangent squared theta plus 1 is equal to cosecant squared theta. Okay, so these are the three Pythagorean identities, and it's also useful to understand the quotient identity, tan theta is equal to sine theta, and just like the other two identities, you can solve for cotangent squared theta if you wanted to. If you move the 1 there, you can see that cotangent squared theta is equal to cosecant squared theta minus 1. So now what I'm going to do here, so I would kind of advocate writing this down. Now what I'm going to do is I'm going to help you guys just solve some identities using these equations, these identities that we already kind of proved. Alright, let's say we want to prove the following identity. 1 over cosine theta plus tan theta is equal to 1 plus sine theta over cos theta. So we recently discussed some of the Pythagorean identities, so I'm just going to write them out, and then we can kind of work through this. The whole point of proving identities is that we have to make the left side of the equation, which is this part, equal to the right side of the equation. Now we know that our Pythagorean identities from the previous lesson was sine squared theta plus cos squared theta is equal to 1. 1 plus tan squared theta is equal to secant squared theta. And we also know that 1 plus cotangent squared theta is equal to cosecant squared theta. Now, we also looked at the quotient identity. So these are Pythagorean identities. But we can also employ our quotient identity. And our quotient identity is basically tan theta is sine theta over cosine theta. Okay, so keep that in mind. Now let's take a look at solving this identity. And rule of thumb, I would always try to look at solving for the side where we have more number of terms, right? Now, in the case that tan is present, I would always try to work with the side with tan, right? Or when you have reciprocal ratios present, I would always work with the side with reciprocal ratios. Now in this case, our goal is, I'm going to work with the left side, but our goal here is to change the left side into the right side. So you want to keep one side constant and you're going to simplify the other side. Now in some cases you might have to simplify both sides. You might have to simplify the other side that you're not working with slightly. But we'll kind of cycle through some of these questions, and I think the best way to kind of learn this stuff is through practice, okay? There's a lot of trial and error here. So anyways, let's take a look at the left side here. So we can notice that the right side is only going to compose of sine and cosine. So that off the bat tells me that I'm going to convert tan according to my quotient identity into sine theta and cos theta. Okay? So off the bat, you can already see that this is basically me solving for the right side. And because the denominator is the same, I can just add these two together and you get 1 plus sine theta over cosine theta. Okay? So this is a pretty simple identity, right? I just wanted to kind of demonstrate to you guys how to solve these things. But you can notice that I've effectively changed the left side into the right side. So your final statement, you can just say, therefore, left side is equal to the right side. You don't have to put an equal sign here. That's just kind of redundant, right? Then for the final statement, you can say, therefore, left side is equal to right side, and you basically proven the identity, okay? So we're going to cycle through a few more questions. I'm just going to demonstrate how to solve some of these identities, and I think the best way is to kind of do different examples, okay? So keep this posted. All right, let's prove the following identity. So I'm going to write down my Pythagorean identities out before I start anything. So my 3 Pythagorean identities, sine square theta plus cos square theta is equal to 1. Right, and you want to try to memorize these. For most cases, you will be asked to memorize them. 1 plus tan squared theta is equal to secant squared theta, and third identity, 1 plus cotangent squared theta is equal to cosecant squared theta. Okay, so those are our 3 Pythagorean identities. I'm also going to write down our quotient identity. So the quotient identity is tan theta is equal to sine theta over cosine theta. Okay, so now what I want to do, if I want to solve for my identity, I want to work with the side that has the most number of terms, right? So let's work with the right side. So this is my right side. Okay, this is my left side. My purpose here, let's change our right side into our left side, right? So working with just my right side here, we can understand that the left side only has cosine. It doesn't have sine or tan. So what I'm going to do here is I'm going to write tan, first of all, using the quotient identity as sine theta over cos theta. Okay? And you can see that you're multiplying sine theta times cos theta times sine theta over cos theta. And you can see that cos theta divided by cos theta cancels out. And then you're left with sine theta times sine theta, which is sine squared theta. Now you can also notice that sine squared theta, using the first identity here, if you wanted to solve for it, if you want to isolate it, because it's an identity, this is always true. So if I move the cos squared theta to the other side, right, you can write sine squared theta as 1 minus cos squared theta. So I can convert this into 1 minus cos squared theta. So it's an equivalent expression. You can actually notice that I've converted my right side into my left side. So your final statement here, you can just say therefore left side is equal to right side, and you've technically proven your identity. Alright, let's prove the following identity. Tan theta plus 1 over tan theta is equal to 1 over sine theta times cos theta. Okay, so I'm going to write down my Pythagorean identities first. And I would recommend to memorize these. So my Pythagorean identities, sine squared theta plus cos squared theta is equal to 1. 1 plus cotangent squared theta is cosecant squared theta, and 1 plus tan squared theta is equal to secant squared theta. Okay, so we also want to conclude our quotient identity. Okay, so our quotient identity is as follows. Tan theta is equal to sine theta over cosine theta. Okay, and what I want to work with here is my right side because it has more number of terms. So it's usually a cardinal rule that I would follow. Sorry, my left side, not my right side. Okay, so let's work with my left side, all right? So working with my left side, you notice that the right side is only going to be composed of sine theta and cosine theta. So I'm going to change my tan theta into sine theta over cosine theta using the quotient identity. Plus, and I'm going to change 1 over tan theta, and you can think about 1 over tan theta as 1 over sine theta over cosine theta, which is technically the reciprocal, right? So if it's reciprocal, you basically get sine theta over cosine theta plus cosine theta over sine theta, because we know that a reciprocal is where you just flip the numerator and denominator, right? Now what you want to do here is I want to make a common denominator. So if I want to make a common denominator, the lowest common denominator between these two denominators is sine theta, cosine theta, okay, which kind of matches what we see on the right side. So having said that, I'm going to multiply this fraction by sine theta, right, and this fraction by cosine theta, because then what's going to happen here is going to get to this denominator. So I'm just creating an equivalent fraction. And once I do this, you can notice here that you'll basically get sine theta times sine theta is sine squared theta over cos sine theta sine theta, plus cos theta times cos theta is cos squared theta over sine theta cosine theta. Okay, now you can see that the denominator is the same, so you can actually make this one collective denominator. And then you basically have sine squared theta plus cos squared theta. Now at this point, you can actually notice that this is actually a part of an identity. This is this identity, it's the first identity, that this is actually equal, sine squared theta plus cos squared theta is actually equal to 1. So having said that, we can actually note that all of this becomes 1, so we actually get 1 over sine theta cosine theta, which actually matches the right side. So then our last statement, therefore our left side is equal to the right side, and we've effectively proven our identity. Alright, let's prove the following identity. 1 minus 2 cos squared theta is equal to sine to the power 4 theta minus cos to the power 4 theta. So let's first write down some of our Pythagorean identities and our quotient identity. So our Pythagorean identities are sine squared theta plus cos squared theta is equal to 1. 1 plus tan squared theta is equal to secant squared theta. And 1 plus cotangent squared theta is equal to cosecant squared theta. Okay, so those are 3 Pythagorean identities. And our quotient identity is basically tan theta is equal to sine theta over cosine theta. Okay, so those are some of our identities that we need to look at. And rule of thumb, you can actually work with either the left side or the right side in this case, right? Because of the fact that they have the same number of terms. But I'm going to work with the right side because of the fact that the terms actually have a power of 4, so you can actually factor it. Okay, so there's a higher level of complexity there. Now the way I'm going to factor the right side is I'm going to use the template a squared minus b squared, which you can factor as square root of a squared plus minus the square root of b squared, which will give you a square root of a squared, which is basically a, plus minus square root of b squared, which is b. This plus minus just implies that we have 2 conjugate factors, a plus b times a minus b. And conjugate factors have the same terms but opposite sign, right? So I'm going to utilize this template to factor out sine to the power 4 theta minus cos to the power 4 theta. So sine to the power 4 theta, I'm going to pretend as a squared. I'm going to square root that, plus minus b squared, I'm going to think about that for cos to the power 4 theta. Okay? And the square root of sine to the power 4 theta is sine squared theta plus minus square root of this guy here is cos squared theta. So our two factors here are sine squared theta plus cos squared theta times sine squared theta minus cos squared theta. Make sense? So using this notion, we can also utilize the first Pythagorean identity. We can understand that sine squared theta plus cos squared theta is equal to 1. So all of this guy here becomes 1. So 1 times sine squared theta minus cos squared theta is what we're left with. And you can notice that this isn't what is seen on the left side. That's because we don't actually have sine squared theta that's present on the left side. Now what we want to do here is we want to get rid of the sine squared theta and just express it purely as cosine squared theta. The way we're going to do this is I'm going to take my first identity, I'm going to move the cos squared theta to the other side because I can solve for sine squared theta. If you do this, if you look at this, you can see that an equivalent expression for sine squared theta is 1 minus cos squared theta. So this is always true because this is an identity, right? So considering this, I can plug that in for sine squared theta. If I do that, you basically will get 1 minus cos squared theta minus cos squared theta. Okay? And having said this, I'm going to collect the like terms, so you get 1 minus cos squared theta minus cos squared theta is negative 2 cos squared theta. Okay, and you can actually see that this is equivalent to the left side. So our final statement here, therefore, left side is equal to right side. And we've actually proven this Pythagorean, this identity, this trigonometric identity. Okay, let's take a look at an example of a Pythagorean identity. So we need to actually prove this in the sense that we have to equate the left side of the equation to the right side of the equation. In order for us to solve this identity, we need to know all three Pythagorean identities. And the Pythagorean identities are as follows: sine squared theta plus cos squared theta is equal to 1. 1 plus tan squared theta is equal to secant squared theta, and 1 plus cotangent squared theta is equal to cosecant squared theta. Okay, so these are our three Pythagorean identities. Okay, it's also useful to understand the quotient identity. Tan theta is equal to sine theta over cosine theta. Okay, now having said this, I'm going to say that the 1 plus cosine theta is my left side, the sine squared theta over 1 minus cos theta is my right side, and your whole point here is to let one side equal the other. So I'm only going to be working with one side. The rule of thumb is you would tend to work on the side with more number of terms or the more number of complex terms. So I'm going to work on my right side here. So I'm going to make the right side be equal to my left side. So we can understand that sine squared theta, if you take your first Pythagorean identity that I wrote out here, if I move the cos squared theta to the other side, right, the sine squared theta can be written as 1 minus cos squared theta. Okay, and you can put this over 1 minus cosine theta. Okay, so instead of writing sine squared theta, I'm going to write 1 minus cosine squared theta. After I do this, you can notice that the 1 minus cosine squared theta, so this portion here, this is like a difference of squares, right? So you can kind of think about it in the form of a squared minus b squared. So if you have an expression in the form of a squared minus b squared, you can actually factor it as square root of a squared plus minus square root of b squared, right? And you basically would get a plus minus b. So one of the factors is a plus b and the other factor is a minus b, right? These two are examples of conjugate factors. So we understand that we can factor 1 minus cosine squared theta as 1 minus cosine theta times 1 plus cosine theta, right? So you can basically do square root of 1 plus minus square root of cosine squared theta. That's going to give you 1 plus minus cosine theta, right? So that's where I got these two conjugate factors from. So this is the numerator, and then I'm going to put this over denominator 1 minus cos theta. You can notice here that there is a common factor of 1 minus cosine theta, and what you can do here is you can cancel out the two common factors. And when you do that, you actually get 1 plus cosine theta. So you can actually notice that the right side is equal to the left side. So our final statement here is therefore the right side is equal to the left side. And we've proven our identity.